Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss RC phase shift oscillator. Let's begin. RC phase shift oscillator is a sinusoidal feedback oscillator in which the feedback network consists of resistors and capacitors. We can understand it. Consider an amplifier. It is the input signal. We obtain the output. In case of RC phase shift oscillator, we use a common emitter amplifier, common emitter transistor amplifier. If we take the input signal, then at output we obtain the amplified signal but out of phase, that is a phase shift. (180°). According to Barkhausen's criteria, to obtain the sustained oscillations, the overall phase shift around that of loop either 0 or integral multiple of 2 pi, means 360°. Here we can use the feedback network, that output, the input to that of feedback network, and that feedback network provide a phase shift of 180°. As a result, the phase shift due to the amplifier 180°, phase shift due to feedback network 180°. Total phase shift throughout that of loop will be 360°. Now 180° phase shift we can achieve by using the feedback network. That feedback network consists of resistor capacitor networks. For one resistor capacitor network, if we take one resistance one capacitor, another resistor, that network, let input voltage Vi, output voltage Vo. As we know, the output voltage Vo leads the input voltage Vi by the phase of phi. Therefore, the phase phi will be tan inverse capacitive reactance divided by resistance R is equal to tan inverse capacitive reactance 1 by omega c, 1 by omega c R, omega tan inverse 2 pi nu at the frequency C R Now the value of phi, maximum value of phi we obtained by taking r is equal to 0. If we put r is equal to 0, then phi will be 90 degree, and that CR network we have 90 degree phase shift. But to take 90 degree phase shift, r must be 0, but in practical situation, if we implement r is equal to 0, then output voltage will be 0. In practical situation, output voltage is not 0. For that reason, we have to take C and R as fixed. As a result, for a particular frequency, we obtain a phase shift, and one CR circuit provide us 60 degree phase shift. Therefore, we can use 3 number of CR circuit to take 180 degree of phase shift. So, inside that of feedback network, we use 3 RC circuit to take 180 degree phase shift. Now, by using that informations, we can easily construct the RC phase shift oscillator. First, common emitter NPN transistor which act as amplifier. R1, R2 as voltage divider bias in order to what? In order to achieve proper biasing, we arrange R1 and R2, RE, CE, capacitance emitter capacitor, CE is called the bypass capacitor. As a AC passes through this and DC is obstructed throughout that of CE, and collector RL. Point potential plus VCC, that one is the amplifier, common emitter amplifier. Then feedback network, 3 RC network, C R C R C, here R dash, that value is equal to R minus SI. Why? In that of input, there will be an input impedance. That input impedance is equal to SIE. Here is the input impedance HIE. If it has the resistance R dash is equal to R minus HIE, so the net resistance is equal to HIE plus R minus HIE. HIE cancel out, the net resistance will be R. Here the net resistance will be R. So R dash we take R minus HIE. That portion is the amplifier, these portions are the feedback network. This one is the circuit diagram of RC phase shift oscillator. We can understand its working. When the supply voltage plus VCC is applied, it processes oscillations. The output oscillations of amplifier is applied to that of RC feedback network. The output of that of oscillation along RL, that is input towards that of feedback network. That feedback network consists of RC network. The NPN transistor in common emitter mode produces a phase shift of 180 degree between the input and output voltages. As I taken it, input and output voltages, there will be a phase shift of 180 degree when we use common emitter NPN transistor. Here we use common emitter NPN transistor. So the phase shift of input to that of output is 180 degree phase shift between the input and output voltages. Each RC section of RC feedback network produces a phase shift of 60 degree. One RC network creates a phase shift of 60 degree. As we take 3 number of RC networks, so the total phase shift from this RC network we have 180 degree. Hence RC phase shift network provides a phase shift of 180 degree. Thus the net phase shift around the loop is 360 degree. Here the phase shift by that of transistor 180 degree plus the phase shift from that of RC network again 180 degree. The total phase shift is 360 degree. In the last section, RC feedback network, the resistance R dash is equal to R minus HIE, as the effective resistance of R dash and HIE is R. R dash we choose as R minus HIE. So the net resistance R dash and that biasing resistance we obtain as R. For that reason we take R dash as R minus HIE. This is the construction and working of that of RC phase shift oscillator. The oscillation is produced due to phase shift, and that phase shift we obtain by taking NPN transistor in common emitter mode of operation plus RC feedback network. The advantage of RC phase shift oscillator, it does not require inductors or transformers, only capacitors and resistors are useful. It can generate very low frequency and it provides good frequency stability. These are the advantages. Next, in case of disadvantages, it provides small output and it is difficult to start oscillation because of feedback is very small, and it is not suitable for HF operation, high frequency operation, that type of oscillator is not useful. Applications, it is used for low frequencies and it is used in AF range, audio frequency range, that type of oscillator we use. Next, mathematically we can analyze how that RC phase shift oscillator responds to the frequency. Frequency analysis. To take frequency analysis, the SC equivalent circuit, we can draw on the SC equivalent circuit for that of RC phase shift oscillator as HIE is a voltage source, that voltage source HRE V output, current source HFE IB, resistance 1 by HOE, and collector we have the load resistance RL, then 3 shear networks 1, 2, 3. Here C R C R C R dash, which is R minus H I E, that one is connected to this. This is grounded. Okay. Right here HRE, reverse voltage gain, is very small. This one is very small. That one is the SC equivalent circuit. SC equivalent circuit of RC phase shift network. Here that portion is very small, and HOE, this is the order of 10 to the power minus 6. Therefore, 1 divided by 10 to the power minus 6, it is very large. So, we can neglect it, or that resistance just act as the open circuit. And now that HIE is added to that of resistance R dash, R minus HIE plus HIE. So, only we have R dash is equal to R. Now, the equivalent circuit, that circuit is changed. Current source that one is neglected, then RL, C, R, C, R, C, R, C, R, C, R, C, R, that R dash is equal to R as HI is added. That is HFE IB. Now, that current source we can change to that of voltage source. How? As if there will be a voltage source and a resistor is connected in series to that of voltage source, then it is converted to that of current source, like this. That of current source, I is equal to V by R, and V is equal to IR. So, I is equal to V by R into R. The potential here is V. By taking that concept, that current source now changes to the voltage source. So, its equivalent circuit we draw. Here is the voltage source, and that voltage source is equal to H Fe, that current, that the base current IB RL. RL, next C R C R C R C R C R C R. Now, the SC equivalent circuit of RC phase shift oscillator is that one. Now, we analyze that SC equivalent circuit. In exam, you can start the analysis by taking that circuit. Let me start analyzing it. Analysis: SC equivalent circuit of RC phase shift oscillator. The voltage source, load resistance, CR circuit. Let in that first loop the current be I1, second loop current I2, third loop current I3, and that the third loop current across that of voltage source SFE RL I3. Now we analyze it. In first loop, we apply Kirchhoff's voltage law. The sum total of voltage around that of loop will be 0. In RL, the voltage drop RL into I1, RL into I1, RL into I1. In capacitor, it is capacitive reactance into I1, capacitive reactance 1 by j omega c. In complex form, J play the same role as iota in that of complex number. Here capacitive reactance in that of complex form 1 by j omega c, 1 by j omega c into I1. Again for R, the voltage drop, resistance into current, R into I1. We can simply analyze it in terms of currents. as there are three currents I1, I2 and I3 in that of three loops, so we can simplify it in terms of current I1, I2 and I3, and the sign notation, if I1 as clockwise then it is taken positive, if it is anti-clockwise then it is taken negative. In that same rule we apply in that loop number 1. Here the current is I1, so the current, the voltage section at RL, C and R are in clockwise direction, RL plus 1 by j omega C plus R I1. Next, here current I2, the I2 current flow across that of R, and it is here I2 from lower to upper end, so it is taken as negative. Next, I3 current as HFE I3 RL. In that loop number 1 we use KVL, and the equation is written in terms of I1, I2 and I3. You can write it like this, or first we can apply what be the voltage drop across each resistances, voltage drop across RL I1, voltage drop across C 1 by j omega C I1, voltage drop across R I1. Next, voltage drop across R by taking the current, and minus R I2, and voltage drop across this source HFE I3 RL, and then simplifying we have that equation. Or by taking the current terms in terms of I1, I2 and I3, what be that voltage drop throughout that of network. Next, at loop number 2, again in terms of current I1, here current I1 flows through that of resistor R, and it is from this direction, we taken negative sign minus R I1. And current I2 flow across R, here R, and it 2R times of I2, and again I2 flow through that of C, so it will be 2R plus 1 divided by j omega C whole into I2, and I3 flow across that of R is negative from lower to upper end minus R I3. Here is the dominance of the current is I2, I3 not the dominance part, I3 is the dominance part in network number 3. Again another convention, dominance part we use positive, not dominance part we taken as negative. In this way anybody can use the sign convention to show that equation. In terms of I1, I2, I3 we use KVL in that of loop number 2 to show that equation number 2. Next, in loop number 3 we apply KVL. Here the I1 factor as 0, I2 drop across that of R minus R I2. Next, I3 drop across R and C, 2R plus 1 by j omega C I3. Now KVL is applied to that of loop number 3. Here in loop number 1, loop number 2 and loop number 3, Kirchhoff's voltage law is applied. Look these three equations. In these three equations, the determinant of the coefficient of I1, I2 and I3 will vanish, because these three currents are non-zero. Therefore, we can write the coefficient of I1, I2 and I3 in the determinant form. Coefficient of I1, I2 and I3 determinant is equal to 0. Now we can solve that determinant. to that of column number 1. In column number 1, here positive, negative, positive. First RL plus R plus 1 by j omega c in first row and first column, first row and first column. Inside that of bracket, these two are multiplied and then subtracted. Multiplying these two, 2r plus 1 j omega c whole square minus plus r square. Next, here negative minus r, second row, first column, these two are multiplied then subtracted, minus r square, 2r plus 1 by j omega c plus hf rl r square is equal to 0. 2r plus 1 divided by j omega c whole square, a plus b whole square, a square plus b square plus 2ab, 4r square minus j square as minus 1 by omega square r square plus 4r divided by j omega c minus r square as usual the terms. Then 1 by j omega c, it is the complex form as 1 by j omega c. It can be replaced as minus j by omega c. Here again 1 by j omega c as minus j by omega c, minus j by omega c. We have equation number 5. From that of equation number 5, we can equate the real parts as well as imaginary parts to 0. From that of equation number 5, first equating the real part of equation number 5 to 0. How the real parts we obtain? The real parts r plus rl whole into 3r square minus 1 by omega square c square minus here r square 2r. Yes, another real part. First we equate the imaginary part. First we equate the imaginary part. Equating the imaginary part of that of equation number 5 to 0. The imaginary part as minus 4r omega c whole into rl plus r minus 1 by omega c whole into 3r square minus 1 by omega square c square plus here the imaginary part r square divided by omega c. Solve it. Minus 4r rl plus r divided by omega c plus that omega c is multiplied 3r square by omega c plus 1 by omega q c q plus r square divided by omega c. Taking that term to left side, all the terms to that of right side. In that of right side term, taking LCM as omega c, then simplifying it, we obtain omega as 1 by c under root of that term. This is the omega. Then the frequency of oscillation, that is omega by 2 pi. Then frequency of oscillation omega is given to us. For sustained oscillation, we put RL is equal to R. Then that expression is changed to frequency is equal to that much. Here the frequency obtained by taking equation number 5, equating that imaginary parts. Next, we can equate the real parts. Equating the real parts, we have that equation, then putting omega square here and simplifying it 1 by 1. we have SFE, forward current gain. This is the condition for sustained oscillation for RC phase shift oscillator. Condition is if RL is equal to R, then FE is equal to 56. For sustained oscillation, RL is equal to R and FE is equal to 56 in case of RC phase shift oscillator. That one is the frequency, this one is the SFE for sustained type of oscillation in case of RC phase shift oscillator. So, here with the help of this video lecture you understand the concept of RC phase shift oscillator, its construction, working, advantages, disadvantages, applications. We analyze it shortly. By taking amplifier and feedback network, how we call it as phase shift network, and why RC network is used to get 180-degree phase shift. Then its AC equivalent circuit, how that circuit is changed, and finally we are dealing with that circuit. That is the analysis of AC equivalent circuit of RC phase shift oscillator. That one is the circuit, and in each loop we use KVL. We have 3 equations. By taking that 3 equations, the determinant is equal to 0. Solving that determinant, from that of equation number 5, we equate it to the imaginary parts. We obtain expression for frequency for sustained type of oscillation. Next, equating it to the real part, we obtain the sustained oscillation as HFE is equal to 56. So, with this useful and informative notes, let me wind up this session. Thank you.